Good afternoon, everyone. So my topic is all about linear congruence. We will talk about the definitions of linear congruence, the theorem in linear congruence, the proof in linear congruence, and I will give some examples about the linear congruence.
So what is linear congruence? So a congruence of the form AX is congruence to B mod M, wherein A and B is integer and X is a variable and M is a positive integer. The solution to a linear congruence AX is congruent to B mod M are all integers X that satisfy the congruence. So in this section, we will see that the study of such congruence is similar to the study of linear Diophantine equation in two variables. So when we say linear Diophantine equation, this is ax minus my is equals to b. The next one is theorem 3.7. Let a, b, and m be integers with m is greater than 0 and am is equals to d. So in this theorem, it says that m is a positive integer, so there is no m that is negative. So when we say am, it is GCD or GCF of a and m is equals to d. So when we say GCF, it is the greatest common factor and GCD is the greatest common denominator. So pareho lang sila. So, if D does not divide B, then AX is congruence to B mod M has no solutions. So, it says that D does not divide B, then AX is congruent to B mod M has no solution. So if we get the GCD of A and M and then we divide it by B, then we get an answer that is decimal or have a remainder. Therefore, there is no solution. So, um, the next one is if D divides B, then AX is congruence to B mod M has exactly D incongruent solutions modulo M. So, if D divides B, it has D solution.
So next is the proof.
So proof, the linear congruence AX is congruence to B mod M is equivalent to the linear Diophantine equation in two variables AX minus MY is equals to B. So the integer X is a solution of AX is congruent to B mod M if and only if there is an integer y with ax minus my is equals to b. So from theorem 3.7, we know that if D does not divide B, there are no solutions, while if D divides B, ax minus my is equals to b has infinitely many solutions given by x is equals to x sub 0 plus m times m divide d times t and y is equals to y sub 0 plus a divides d times t. So where x is equals to x sub 0 and y is equals to y sub 0 is a particular solution of the equation. The values of x given is x is equals to x sub 0 plus m divides d times t are the solutions of the linear congruence, so there are infinitely many of these. So to determine how many incongruent solutions there are, we find a condition that describes when two of the solutions x sub 1 is equals to x sub 0 plus m divides d times t sub 1 and x sub 2 is equals to x sub 0 plus m divides d times t sub 2 are congruent modulo m. So if these two solutions are congruent, then x sub 0 plus m divides d times t sub 1 is congruent to x sub 0 plus m divides d times t sub 2 mod m. Subtracting x sub 0 from both sides of this congruence, we find that m divides d times t sub 1 congruence is congruent to m divides d times t sub 2 mod m. So now, m and m divides d is equals to m divides d. Since m divides d all over m, so that by theorem 3.2 in the previous lesson, we see that t sub 1 is congruent to t sub 2 mod d. This shows that a complete set of incongruent solutions is obtained by taking x is equals to x sub 0 plus m divides d times t, where t ranges through a complete system of residues modulo d. One such set is given by x is equals to x sub 0 plus m divides d times t, where t is equals to 0, 1, 2, 3, and so on. So, for example, to find all solutions of 9x is congruent to 12 mod 15, we first note that since 9 and 15 is equals to 3, so 9 and 15, the GCF of this is 9 is equals to 1, 3, and 9. And for 15, it is 1, 3, 5, and 15. So, the greatest common denominator or the greatest common factor of these two is 3. So, and 3 divides 12. There are exactly 4 incongruent solution because 3 divided 12 is 4. We can find this solution by first finding a particular solution and then adding the appropriate multiples of 15 divided 3 is equals to 5. So, to find a particular solution, we consider the linear Diophantine equation where is ax minus my is equals to b. So, in this example, we have 9x minus 15y is equals to 12. So, now we will proceed to the Euclidean algorithm. So, we will have 15 because this is the greatest number in linear Diophantine equation. So 15 is equals to 9. So 15 divides 9 is equals to 1. So we get 1 by multiplying it in 9. And 15 divides 9 is equals to 1 and it has a remainder of 6. So para gawin natin to, we have 15 is equals to 9. So, 15 divide 9 is equals to 1. So, ang 1, ita-times natin sa 9 times 1. And the remainder, we will add the remainder. So, 15 is equals to 9 times 1 plus 6. So, now we will proceed to the second and we will get 9 and then the remainder. So, 9 is equals to 6. So, 9 divided 6 is equals to 1. So, 9 is equals to 6 times 1 plus 3 because this is the remainder of 9 divided by 6. So, in the third one, we will get the 6. So, 6 is equals to 3. So, 6 divides 3 is 2. So, we will get 6 is equals to 3 times 2. So, the next one, we will use the back substitution. So, we will get the remaining. So, 3 is equals to 9 because 9 is equals to 6 times 1 plus 3. Diyan natin kukunin yung pag-back substitution. So, we have 3 is equals to 9 minus 6 times 1. So, 3 is equals to 9 times 15. Kasi, yun yung pinakauna nating ginawa. Yung 15 is equals to 9 times 1 plus 6. So, 3 is equals to 9 times 15 minus 9. So, combine like terms tayo. So, 3 is equals to 9 minus 15 plus 9. So, we will have 3 is equals to 9 times 2. Kasi dalawa yung 9. Minus 15 times 1. So, para makuha natin yung yung constant na 12, we will multiply it by both sides. So, we will multiply it by 4. So, 4 times 3 is equals to 12. And, wag na natin gagalawin yung 9 and 15 kasi sila na yung sila yun na yung nag-stand doon sa variable ng x and y. So, 4 times 3 is equals to 12. So, 12 is equals to, copy lang natin yung 9. So, 4 times 2 is equals to 8. Minus, copy lang natin ulit yung 15. Then, 4 times 1 is equals to 4. So, the final answer is 9 times 8 minus 15 times 4 is equals to 12. So, the next one, we have here the 4 incongruent solutions. So, from the proof of theorem 3.7, we see that a complete set of 4 incongruent solution is given by x is equals to x sub 0 is congruent to 8 mod 15. So, the next one is x is equals to x sub 0 plus 5 is congruent to 3 mod 15. Since we already have the value of x and y, and in the linear congruence, we are just looking for x, then we can disregard the y value. So, 9x is congruent to 12 mod 15. So, we have 4 incongruent solutions. So, the first one is x is equals to x sub 0 is congruent to a 8 mod 15. So, since we already have the value of x, we can say that x is congruent to 8 mod 15. So, now we are looking for incongruent system. So, we just have to find from the value of 0 up to 4. So, t is equals to 0, 1, 2, 3, and 4. From the proof of theorem 3.7, we see that a complete set of 4 incongruent solutions is given by x is equals to x sub 0 is congruent to 8 mod 15 because 5 times 0 is 0 plus 8. So, kaya naging 8 siya. So, that is our first solution. The second one is x is equals to x sub 0 plus 5. 5, galing siya doon sa m divides d. So, ito ay 15 divides by 3, kaya nagkaroon tayo ng 5. So, 5 plus 8 is equals to 13. Kaya nagkaroon tayo ng x is equals to x sub 0 plus 5 is congruent to 13 mod 15. So, that is our second solution. The third one is x is equals to x sub 0 plus 5 times 2 is congruent to 18 is congruent to 3 mod 15. So, yung 5 times 2, yung 18 galing siya sa 5 times 2 is equals to 10 plus 8. So, ito ay equal sa 18. So, we have x is equals to x sub 0 plus 5 times 2 is congruent to 18 and congruent to 3 mod 15. So, 3 lang kasi hanggang mod 15 lang. Kaya, hindi naman kasali talaga yung x is equals to x sub 0 is congruent to 23 is congruent to 8 because it is not congruent or incongruent in mod 15.
So next is inverse of A modulo M. So when we have an inverse of A modulo M, we can use it to solve any congruence of the form AX is congruence to B mod M. So to see this, let inverse of A be an inverse of A modulo M so that A inverse of A is congruent to 1 mod M. Then if AX is congruent to B mod M, we can multiply both sides of this congruence by inverse of A to find that inverse of A times AX is congruence to inverse of AB mod M so that x is congruence to inverse of AB mod M. So we can now proceed to theorem. If A and M are relatively prime integers and M is greater than 1, then an inverse of A modulo M exists. Furthermore, this inverse is unique modulo m. This means that there is a unique positive integer of inverse of a less than m that is an inverse of a modulo m, and every other inverse of a modulo m is congruent to inverse of a modulo m.
So for example, find an inverse of 101 modulo 4620. So first, use the Euclidean algorithm to show that the GCD of 101 and 4620 is equals to 1. So this is the Euclidean algorithm process. So 4620 is equals to 101. So 4620 divides by 101 is 45. Kaya ang magiging process nito is 4620 is equals to 101 times the quotient plus the remainder. Kaya nagkaroon tayo ng 4620 is equals to 101 times 45 plus 75. So, kukunin naman natin yung pangalawa, yung 101. So, 101 is equals to the remainder. Kukunin naman natin yung remainder, i-divide natin siya sa 101. Kaya 101 divide by 75, meron siyang 1. And may 26 siyang remainder. Kaya ang gagawin natin, 101 is equals to 75 times 1 plus 26. Ganon din yung process hanggang baba. Kaya nagkaroon tayo ng 75 is equals to 26 times 2 plus 23. Tapos, yung next, nagkaroon naman tayo ng 26 is equals to 23 times 1 plus 3. And the next one is 23 is equals to 3 times 7 plus 2. And 3 is equals to 2 times 1 plus 1. And then 2 is equals to 1 times 2 plus 0 kasi wala na siyang remainder. We will now proceed to the back substitution. So we have now here the 1 is equals to 3 minus 1 times 2. So galing naman siya sa second to the last ng Euclidean algorithm which is 3 is equals to 2 times 1 plus 1. So proceed naman tayo. 1 is equals to 3 minus 1 times 23 minus 7 times 3. Yung 23 minus 7 times 3, galing naman siya doon sa 23 is equals to 3 times 7 plus 2. Doon sa third to the last of Euclidean algorithm. So, it is equals to negative 1 times 23 plus 8 times 3. Kasi ginawa natin 3 minus 23 plus 7 times 3. So, yung 3 times 1, and then 7 times 3, combine like terms tayo. Kaya nagkaroon tayo ng 3 times the quantity of 1 plus 7 minus 23. So, all in all, we have 3 times 8 minus 23 times 1. So, now proceed. Pareho lang siya hanggang makuha natin yung inverse ng modulo ay ng 101 modulo 4620. So, the next one is 1 is equals to negative 1 times 23 plus 8 times the quantity of 26 minus 1 times 23. So, galing naman siya doon sa sunod sa 23 sa Euclidean algorithm sa taas. Kaya nagkaroon tayo ng 26 minus 1 times 23. So, it is equals to 8 times 26 minus 9 times 23. So, now we will have 1 is equals to 8 times 26 minus 9 times the quantity of 75 minus 2 times 26. So, it is equals to 26 times 26 minus 9 times 75. So, we will have 1 is equals to 26 times the quantity of 101 minus 1 times 75 minus 9 times 75 is equals to 26 times 101 minus 35 times 75. So, kaya nagkaroon tayo ng 1 is equals to 26 times 101 minus 35 times the quantity of 4,620 minus 45 times 101. So we will have negative 35 times 4,620 plus 1,601 times 101. So our Bezot coefficients is negative 31 and 6,001. So 6,001 is an inverse of 101 modulo 4,620.
So the last one is proposition 3.4. So let P be prime. So any number basta prime siya. So the positive integer A is its own inverse modulo P if and only if A is congruent to 1 mod P or A is congruent to negative 1 mod P. So if A is congruent to 1 mod P or A is congruent to negative 1 mod P, then A squared is congruent to 1 mod P, so that A is its own inverse modulo P. So conversely, if A is its own inverse modulo P, then A squared is congruent to A times A is congruent to 1 mod P. Hence, P divides A squared minus 1, since A squared minus 1 is equals to the quantity of A minus 1 times the quantity of A plus 1. Either P divides the quantity of A minus 1 or P divides the quantity of A plus 1. Therefore, either A is congruent to 1 mod P or A is congruent to negative 1 mod P. That would be all. Thank you for listening.